You have 5 minutes to pack your bags. What are you going to take? Maybe some hiking boots for your sister's wedding in New York, or glass slippers for your hiking trek in the Himalayas. The point is that what you are going to pack depends on the purpose of your trip. I want you to keep thinking about that and try and think if you can figure out how it connects with the rest of this talk. My name's Paula Ta-Shma. I'm from IBM Research, and Guy Gerson and I are going to be talking about pluggable Spark SQL filters and how they can help GridPocket users keep up with the Joneses, meaning their neighbors, and at the same time save the planet. Okay, so what would actually convince you to reduce your energy usage? Maybe it would be to save money. Raise your hand if that would convince you. Okay. What about saving the planet? Raise your hand. Would that convince you? Really? Okay. It turns out that research shows that the answer is a good dose of healthy peer pressure. So this is really a win-win situation, because by comparing ourselves with our neighbors, anonymously of course, this can help us both save money at the end of the month and save the planet. So that's our aim here. In this talk, we're going to try and help GridPocket, a smart grid company based, headquarters based in France, help their customers do that. Okay, so GridPocket manages data for utility companies, and the data can be gas meters, electrical meters, water meters, and so on. They developed an open source data generator which closely matches their customer workload. So our target is to be able to manage data from 1 million meters. Each meter is reporting data every 15 minutes, and records are about 100 bytes each. So we generated 1 terabyte using their data generator, which represents around 3 months worth of data. Now, if we allow for 1 order of magnitude growth in each one of these dimensions, so instead of 1 million meters, say 10 million meters, and same for each dimension, we're going to end up with 1 petabyte of data in 3 months. So what does this mean? This means we really need to use object storage to store that data, because your typical database is not going to scale to that level, and also your typical database is going to be at least an order of magnitude more expensive to store the data than object storage. Now, our data set that we're using, the one that is developed by GridPocket and generated by the generator, is generating one large denormalized table with meter readings. So what we're going to do is we're going to use SQL queries on that data set to compare a users with their neighbors and compare their energy consumption with the average of their neighbor energy consumption. Okay, so I talked about object storage. Say we have to use object storage for really big data. So let's give a little bit of background about that. And objects are kind of similar to files, but there are some really important differences. So objects contain data and metadata. Well, that's kind of like files. But objects are written once and never modified. So you cannot append data to the end of an object. And you also cannot update an object in place. On the other hand, you can override an object completely, and you can update its metadata. But on the other hand, there is no rename operation for an object. So if you want to change the name of an object, you better write it out again from scratch. Now, object storage is accessed through a RESTful API. So you have the typical put, get, post, and delete operations, which can work on objects or also on buckets, which are object containers. So there's a flat namespace, but it's really 2 levels. You have the bucket level, and then you have the object level. Now, object storage is famous for giving high capacity at low cost, and it really is the storage of choice for truly big data sets. Analytics works best on objects which are not too small and that roughly equally sized. So examples are Amazon S3, IBM Cloud Object Storage, Google Cloud Storage, and the open source OpenStack Swift. Okay, so now we're getting back to our topic of analyzing data on object storage using Spark, and in particular we're going to be using Spark SQL. Now, just want to point out that today it's common practice to run storage and compute, or object storage and Spark, as completely separately managed microservices in the cloud. This is quite different, I want to point out, from the way the Hadoop ecosystem originally started out, where you would have HDFS and MapReduce running on the same hardware in the cloud, and a lot of effort was put in to allow MapReduce computations to be run very close to the storage it was operating against. But today I'd like to argue that the common wisdom is that these are separate microservices, should be managed separately so that they can scale separately, and also because object storage, or storage in general, probably needs different hardware, storage-rich hardware to run on, and compute needs compute-focused hardware to run on. Okay, so we want to query data on object storage directly. We don't want to have to bring, big pieces of the data from object storage into a database engine, index the database, and then run queries on that. We want to run directly on object storage. But there's lots of data out there, and by having it on separate microservices, it means that we're actually going to ship data from the storage into Spark in order to run the queries, right? And that is going to cost us. So our goal here is to minimize the number of bytes shipped across and minimize the number of REST requests that need to be run. And these are the key factors affecting the cost and performance of the system. And just keep in mind, this could even run across the WAN, where things are going to be even more important. So how is this done today? So first of all, you'd use specialized formats like Parquet and ORC. First of all, these gives you column-wise compression. Obviously, less bits stored, that's less bits to send across the network. Secondly, you have column pruning. So with Spark, you only need to ship those columns that are relevant to the query. And thirdly, you have specialized metadata facilities. But we want one solution for all data formats. So besides Parquet and ORC, we also want to be able to handle JSON, CSV, proprietary formats, everything else. A technique which actually works across all formats is Hive Style partitioning. And this relies on a dataset naming convention. So for example, I said already that object storage has a flat namespace, but we can create a kind of virtual folder hierarchy by using slashes inside object names. And we can use object names to encode something about what data is actually in the objects. So for example, with the date field, we encode it inside the object name. As you see here, there's a list of objects here. We have the bottom half here of objects from the 22nd of August, the top half from the 21st of August. So if I'm querying for the 21st of August, obviously these bottom objects are not relevant to the query and I don't need to ship them. Okay, so that's all great. It's a great technique, but it has its limitations. So only one hierarchy is possible. It's a bit like in a database having only a primary index and no secondary indexes. Another limitation is that if you decide to change the partitioning scheme, you need to rewrite the entire data set if you're using object storage, because as I already said, in object storage, there is no rename operation. Also, there's no range partitioning. So this kind of technique supports partitioning with discrete types, like say gender, male, female, so on, dates, ages. It doesn't work well for arbitrary floating point numbers like timestamps, longitudes and latitudes, and so on. So finally, a deep hierarchy, if you're going to try and encode, date and then city and then a whole bunch of fields in there, you'll end up with a deep hierarchy, and this can give you small object sizes and non-uniform object sizes, and this is going to be bad for performance. Okay, so can we do more? And as you may have guessed, the answer is yes. And I want to remind you what I said in the beginning of the talk, which is, okay, what you're going to take, what you're going to pack in your bags really depends on your travel destination, okay? So think of objects as things that you might want to pack with you when you travel. And what I'm talking about traveling here is, okay, we have a query, we have a destination, so traveling is traveling from object storage across the network into Spark. So here, what would you do? So just imagine, okay, you're going on a trip, you know where you're going, but now your place may look a bit like my place, which is, it's kind of like a huge warehouse full of stuff. How are you going to find what you need for your trip just in 5 minutes? So what would you do? You'd use package labels, right? And you'd probably index your stuff so that you could quickly find it in 5 minutes. So that's exactly what's going to work here for big data as well. We're going to use metadata. That's going to be package labels for our objects. And we're going to index that metadata so that we can quickly find which objects are relevant to a query and ship only those objects across to the Spark cluster. Okay, so what do? We generate metadata per object column. So just remember, an object can contain thousands of rows inside, and it's tabular data, so there are different columns, and we can generate metadata per object column, and we index it. There are various index types, and we're going to filter the objects according to this metadata. So this is going to apply to all formats, so JSON, CSV, as well as Parquet and ORC and your own proprietary formats, whatever. So example, just say we have an object, could have thousands of rows in it, but we're going to keep the minimum and maximum values for that column. So if it's temperature, we might have minimum 7.97, maximum 26.77 for that object. Okay, another example is geospatial data. We're going to keep something like a 2-dimensional minimum and maximum, so that's a bounding box. We can keep the top left and bottom right coordinates, and that will track, the bounding box of all the data points inside the object. Another example is, say, for a city column, we could keep the entire set of all the cities inside the object. Okay, so we're going to filter according to this metadata. We store one metadata record per object. This is unlike a database fully inverted index. For a database, you have one index row per each original row in the table. But here, one object could contain thousands of rows, and we're just going to keep one piece of metadata for each object in our index. So the index is going to be a lot smaller than the data. This is important for really big data sets. We have various index types, so as I mentioned, min, max, bounding boxes, and the value sets I mentioned before, well, they can get very big depending on the data set, but you can use Bloom filters as space-efficient ways to do that. Now, users can choose which columns to index. You don't have to index everything, and you can choose which index type you would like per column. And you can index additional columns later on if you decide, or if it turns out later on that that would be beneficial. The main requirement is no false negatives. So if you bring data from object storage into Spark and it's not relevant to the query in the end, that's okay, because it's all going to get filtered out by Spark anyway. But if there is data that is relevant to a query, you must bring it. If you leave it in object storage, you're going to be missing some of your query answers, and that's bad. So no false negatives are allowed. Now, this technique avoids touching irrelevant objects altogether. So unlike Parquet, for example, it has metadata in the object footer at the end of the object. So in order to get to that metadata, you actually need to go and read part of the object. Whereas our technique, you figure all this out before you even go to object storage. You only need to touch the relevant objects. Our technique also handles updates. So for example, just say you've got your metadata index set up and you go and add another object, you delete a few objects, but you haven't got around to updating the metadata index yet. Everything's fine as long as we make sure we're only filtering out irrelevant objects. Okay, so how is this implemented? So on the left, here you see a typical Spark SQL query execution flow. So there is a partition pruning stage, which figures out what partitions can be pruned before going and reading the data, say from object storage. Now what we did is we added a new interface in Spark which allows you to add arbitrary filters, which can be application specific, and that interface can be called after the partition pruning stage. So what this means is that all the goodies that work in Spark today still continue to work. Use the partition pruning, use Parquet, everything else, but in addition you can do additional filtering. So we implemented our interface using a metadata filter that I've told you about already. We've implemented it using Elasticsearch, but any other kind of component could be used instead. And that does additional filtering before going to read the data from object storage. Okay, so this is what the interface looks like. What there is, basically you need to write a function, can be completely application specific, which says it's Boolean. It either needs to say, yes, we need the object, or no, the object can be filtered out. And there are two parameters here. One gets a sequence of filters. That's basically the query constraints you get from the SQL query. And the other one is a file status object, which contains the object name and also contains other information that's known about the object. Now to integrate all this into Spark took under 20 lines of code for the interface. So our implementation, which implements the interface, is obviously more code than that, but the interface itself, its integration into Spark is less than 20 lines of code. Okay, so now I'm going to switch gears a little bit. We talked a lot about querying data and metadata and so on, but the question is, now I'm going to talk about data ingestion and preparing that metadata, because obviously you need to generate that metadata from somewhere. And if you assign records to objects in a totally random way, then your metadata may actually not be that meaningful. So you need to do an ingestion phase anyway. While you're doing that, can you do something smart? Assign data records to objects in an intelligent way so that metadata is as meaningful as possible. Okay, So I'm going to talk about doing this with Kafka, and Kafka allows you to define a user defined partitioning function, which should be stateless in order to be scalable as possible. And we research various ways in doing this, and I'm going to talk about the grid partitioner, which is how we did it for the GridPocket use case. We divide the world map into a grid. The precision depends on the use case. And each data point belongs to a cell in that grid. Each cell is hashed to a partition. You see the partitions here in purple. And a partition can contain multiple cells. Partitions will periodically generate objects. So you can have objects which cover data from multiple cells. And each object is described then using a list of bounding boxes, one for each cell. So like you see here, an object can contain more than one cell, so you have a list of bounding boxes, and that's its metadata. Now I'm going to give you some experimental results on what we did. So I told you we generated around a terabyte of data representing 3 months worth of data. I told you about the data set. We used the grid partitioner using precision 1, which means cells are roughly 10 square kilometers. And we compared using 50 and 100 Kafka partitions. And the query below is comparing me with my neighbor's usage. And what we see here is this yellow part, that's the important part, which is doing the geospatial constraints, and that's what dictates how much data I'm bringing from object storage. So that's the part that we ran for the experiments. Okay, so some experimental results. On the left is no filter at all. And that's the same, doesn't matter what query we ran, it came out the same. So I'm just doing it once. And the next 3 sets of bars are for 20 by 20 kilometers, 10 by 10, and 5 by 5. And as you see, the blue is 50 partitions, red is 100. You get better performance for 100 partitions because you have slightly, each partition handles less cells, and so you get better metadata quality. But the main point here is that we are able, by using the filters, when you actually need less data for your query because the bounding box is smaller, you are able to bring back less data from object storage to Spark, and that's the main thing we wanted to achieve here. And if we measured the number of GET requests, we see exactly the same pattern again, and same for the amount of time taken. So this is additional evidence that, yes, measuring the number of gigabytes transferred and the number of GET requests is also giving us the same as the performance, the amount of time that queries took. So now Guy Gerson is going to present a demo running on, instead of 1 terabyte of data, it's 11 gigabytes of data representing 1 day's worth of data. Same queries you said as you saw before.
Okay, so hello everyone. Thank you, Paula. I will follow a Jupyter notebook. This notebook actually has some rendered visualizations, so it's pre-recorded and edited just to save us this time. And oh, you already started it. I want to start it from the beginning. Okay, so we start by initializing a wrapper class. This will allow us to monitor the execution of our queries. And we load our data, which is 1 day of GridPocket simulated data. We can see a sample of it. And we can also visualize the location of each of our meters on the map. We can see some clusters in more densely populated areas. I think you can just move it. Okay, so is it running? Yeah, so we would just select a random meter. This meter would represent a user for the rest of this demonstration. Yeah, so we're interested in this user and checking how it compares with its neighbors. So we would define the neighborhood of this user as a bounding box of 5 kilometers around it. And each meter that we find inside this bounding box would be treated as its neighbor. And we can see we get a really nicely shaped rectangle as the neighborhood. So once we found the neighborhood, we can start comparing some statistics of the user with its neighbors. So for example, if we check the energy consumed today by the user, we can see it in green. Compared to the average in the neighborhood, we can see our user isn't so energy efficient since he's consuming more electricity today than the other houses in the neighborhood. Okay, so things get interesting if we check which meters did we needed to scan in order to find this small neighborhood. And we see that basically we scan all of the meters in our data set. So now we'll do something else. We will plug in our implemented filter. We do it by a simple SQL configuration. And now we run the exact same query again. So again, we build a 5 kilometer bounding box around our user. And we can see we find the same nicely shaped rectangle as the neighborhood. So it looks exactly the same to the result we got without the filter. But the picture starts to look a bit different if we will check which meters did we needed to scan this time in order to find the small neighborhood. And what we see is that when the filter was activated, we only needed to scan this small region of France in order to find the relevant meters to the neighborhood. So how did this happen? Well, during the ingestion phase, we map each meter to a certain partition by its location. So we can see the colors of the meters which show the partition this meter belongs to. And this gives us really nice spatial locality inside of our objects. This is Paris, by the way. So as you can imagine, this really affects the performance. And if we compare the performance of the two queries, which is the same query we just did, in green we see with the filter, and in red we see without the filter. With the filter, we had only 3 GET requests to the object storage compared to 124 without. And also using the filter, we shipped less than 200 megabytes from the object storage compared to almost 11 gigabytes which needed to be shipped when not using the filter. And the same we see for the execution time. So the execution with the filter took less than 5 seconds compared to over a minute without the filter. And in total, we scanned less than 20,000 meters compared to a whole million. And remember, each meter has a lot of data samplings. Okay, so if I summarize the performance we just see for this example query, we've seen a 13-factor improvement in processing time, and we saw 56-factor improvement in the byte ships from the storage. So this is a really huge difference. So if I would just wrap it up, we can see this technique can really give us significant benefits to performance. As well, I hope this demo helped better understand the use case and the work we did. And back to you, Paula, for conclusions.
Okay. Okay. Can't seem to switch back. How do I start that? We have to get that off. Okay. Okay, so conclusions. This is the last slide. Don't let your vacation turn into a relocation. When you go on vacation, it's not feasible to pack up your whole house and travel. The same way, when you're running SQL queries directly on object storage, you need as many techniques as you can get your hands on to limit the amount of data you can pull out of object storage and pull into Spark. Small change, dramatic improvements. We focused on geospatial and GridPocket, but this applies to multiple use cases and data types. Finally, IBM's investing in Spark SQL. If you'd like to get your hands on that, then talk to me afterwards or to Torsten, who's sitting over there. And that's it. Thanks.
Wow, thank you. I think we have time for one more question. Does anybody have a question? No? Okay, awesome. Thank you so much.